We did already talk about it being a plug and play and future-proof control system. But what design considerations have gone into making it easy to integrate with existing mechanical systems?
I often say there's nothing more manual than industrial automation, right? Because the sheer quantity of engineering hours that are needed to integrate all of those systems with one another, right? Not only you're taking perhaps actuator from one brand, robot from another's, PLC from a third brand, safety system for the fourth brand, and integrating all of those into working system is quite complex. It requires a lot of engineering hours. I think machine motion goes at the very problem of this and making all of those things plug and play from the get-go, removing a lot of manual time, right? So if you're a system integrator, if you're a machine builder, you're actually making your profit more profitable by doing so. The footprint also of the device is much, much smaller. So you no longer need to reserve the space for those, again, bigger cabinet-based system that needs to be, custom designed, custom assembled, and custom programmed anymore. So I think it's quite of a fundamental change around how those cells are designed. There's just less engineering content. Engineers can focus on the products and less so on manual, tedious works of wiring, for example.
So you mentioned the 3,000 watts for 30 motors. So how does the controller handle the complex motion control for those multiple motors?
Yeah, no, it's a fairly an important point. Like if you go in the context of intralogistics, for example, you will see those warehouses with very complex conveying system where you need to do sorting, accumulation, pacing, and all of this requires different conveyor section, different routing, and you'll mix perhaps a pneumatic system to push boxes left or right. Perhaps there's a vision. All those systems are fairly complex, and if I rewind back just a few years ago, creating those systems with Vention technology was very possible. Well, you might need 4 or 5 machine motion working in unison. Today, we can redo those systems with a single machine motion AI, right? Delivering significantly more power and significant more simplicity at the same time because you no longer need to have all those motion controller being orchestrated with one another. So it brings a lot of simplicity. There's an aspect in there that is quite also important from a wiring perspective. Any machine builder knows that wiring is actually not a trivial task, and you need to think about where the wire will go, about a bending radius, and about all those technology consideration. But all those motors for machine motion AI are daisy chainable, which means you never need to go back to the drop point to power the next motor. You can simply power your motor from the previous one that is next to it. So it makes cabling or routings of those wires significantly more simpler. You need less wire to complete your own machine, which brings costs down to some extent. So again, you now have a device where you can do complex intralogistics system or assembly lines with very little wiring. And the power of this is all that configuration around which motor does what and so on is now entirely software defined. And that contrasts a little bit with a hardware defined world where the way to tell a motor to turn left or to turn right is to make sure you wire the each side in the right terminal block. When you start to work with more abstracted system like machine motion, you shift to a software-defined world, which it makes it easier to support, easier to maintain. You can remotely connect and adapt the configuration of the machine because it's always software-defined. So you bring even more simplicity from that perspective.
Can you describe a scenario where the AI features of machine motion AI improve robotic or machine operations in a way that benefits the mechanical design choices?
AI will change how we're thinking about robot cell design. And let me explain, right? Today, in a given robot cell, you might have 50, 60, 70, hundreds of sensors to do the orchestration of the various tasks within the robot cell. In a future, instead, you might have 1 or 2 high ceiling camera, and we're using a completely software-defined approach to do this entire orchestration as opposed to relying on sensors. Instead of having a PLC, you will have GPU. instead of having very prescriptive and high precision jigs and fixtures, again, you'll have a camera on the robot to figure out where the part is in the unstructured space. So all those change, if you think about them, the fact that you no longer need a fixture, the fact that you no longer need hundreds of sensors, but instead a camera, the fact that you no longer need a custom automation cabinet, but perhaps a GPU-based control devices will bring costs down and will bring affordability up for more and more people. So the robot cell of the future is simply a simpler robot cell, right? It's going to become simpler. And more of the consideration we've been thinking of as mechanical engineers, and I'm one of them, I've designed a lot of those equipment myself, will shift to software consideration as opposed to mechanical consideration in an AI-defined world. So I think this is quite of an inflection point. And um, there's a quote from Bill Gates that I really like. He says, we tend to overestimate the change that will happen in the next 2 years, but to underappreciate the change that happened in the last 10. And I'm not saying that AI will change everything tomorrow or perhaps in 2025, but I think we'll see probably in the next 3 to 4 years how those newer design of robot cell, those more simpler design will start to percolate down the factory floor.
Are you able to put a statistic on the disparity of spending the money mechanically as opposed to with the all the technology that's needed for the software implementation and integration?
It's an excellent question, and I wish I had a very 0-1 answer. I don't, but I can give you like nuggets to think about this.
Okay.
Today, a camera that is augmented by our proper foundational model will cost you around $600, right? If you think about a jig and fixture that you would need to position in a structured fashion that same part, might cost you $2,000 to $10,000, right? So we're talking about like a four, almost for certain components, almost a 4 or 5x difference in cost. Now the full robot cell, you still need a robot, which is a big, cost for the robot cell. You still need, safety devices, which but you would probably expect all of those pockets of saving to translate in a 20%. And sometimes this can make the difference between a payback of a year and a half to a payback below 1 year. And that's really, really important because I think we're not far away from being able to provide in a consistent fashion a 1 year payback to manufacturers. And that's quite an important point because if you know as a manufacturer, you're going to put the capex down and recoup that investment in the same fiscal year, you become more indifferent between investing in software only versus investing in hardware software, right? As soon as you're below that 1 year threshold in the mind of the CFOs and the financial controllers of those businesses. So we're not far away. I think AI will help with that. And we'll have probably Sharon to play the movie together in the next 2 or 3 years to see what type of cost saving does that bring to those equipment, which I think would be very good for you American manufacturing.